Hi everyone. Today we are going to start to a new topic about the frequency response in control system theory. Okay? And so in the section 1 we need to define the R problem in the control system. Okay? And so first of all we need to give the concept of frequency response. We have dealt with the transfer function, S domain, and the other things related to the what are generated output response based on these features. But up to now, we have only two concerns about the systems: the transient plus steady state always be rearranged with the PID controller or the another techniques which is given in the root locus 1, right? But in these cases we always apply the system to the unit step or ramp or parabola signal, especially for the steady state error cases. But these signals can be summarized as with the frequency of these signals always equals to the 0. Okay? And so the transfer function generates to output, but based on the unit ramp and parabola. Okay? And so we can easily calculate the steady state error in here when the frequency is equals to the 0. And so this is the easy way to create your control system. But in the real life application, we may utilize the frequency signals or the input signals or a reference signal, even if in the closed loop transfer functions. Okay, this are the basic problem in here. Because the transfer function has the poles with the specific frequency values in the S-plane, and so it responds to the frequency signals as an input or the reference signal in a different way. And so we need to analyze beside from the transfer function as the input one. Okay, and so the input signal types or the frequency can have effects on the transfer function due to the nature of the frequency domain. Okay, and so assume that in order to understand the problem, assume that we have the K, C, and M in here. This is the mass spring damper system, and so we can define the X deflection rate in here with the FD, the force, and then we can apply or assign the FD as the unit step response. And then we will have this kind of output in here, XT and T, and so we have the reference point in here just like this one. This is the 1 because it's the unit step, and so we may have this kind of output in here. And also we can say that this case is directly related to a transient response, but the other term is the steady state one, right? This is the condition of the second order system or the first order system. This response coming from the natural solution of the R system, like the XS can be rewritten as the K1 divided by S plus K2S plus K3 divided by the second order approximation system. Okay, But this is our solution. Every solution given in this format, and then this must be equals to this one. Okay? And also we can say that this part has the transient effect on the system, but this is coming from the unit step response, because we have the k1 divided by s, and so it creates to the steady state solution of these terms. Okay? And so this unit step directly determines the output, even if we diminish the transient response one. Okay? And so in time this transient is diminished, and then we will have only this part, the unit step signal, at the output of the R generated signal, or the transfer function output. Okay? This is the basis of the R system. But just remember that the unit step, ramp, or the parabola does not contain to the frequency pattern at this case. Okay? And so we will iterate the R problem in here. Suppose that we have sinusoidal signal like the ft can be equals to the f0 times sinus wt. Okay, w is the angular frequency of these terms, and so our output in S domain can be rewritten as the xs is equals to the omega n square divided by s square plus 2 zeta omega n s plus omega n square times w. f0 is the magnitude of these terms, and so s square plus omega square in here. Okay? And so this is coming from the sinus signal. This is our transient response in here. In partial fraction form, we have the xs is equals to the k1s plus k2 divided by s square plus omega square plus k3s plus k4 divided by s square 2 zeta omega n s plus omega n square. Okay? And so this is considered as the with the previous knowledge, this is the transient response. But this is this is the sinus signal, right? And so this, in this case, this also diminished in time, but this sinus signal always preserves its energy to the to the input, the R system. Okay? But we have basic difference in here, which is we have the angular frequency, or the frequency pattern of this signal. And so this affects the performance or the outputs of the R transfer function, or the system representations. Okay? And so similarly, the output has the frequency like this one, right? Because in the first case, we generally write the k1 divided by s, right? And so this creates the unit step in the steady state condition. But in this case, we always changed in the input signal, which creates or causes to our output possess the frequency characteristics, right? And so how we can define this information in here? First of all, we need to give the reminders in here, just like this one. The remember one is the one condition. The Euler identity gives us the general solution of sin and cos signal, just like this one. And so we have the real part in here, and we have the imaginary part in here, and also we can build what the other identity in here. But in this case, we can draw the magnitude of this signal with represented by the m, and also we can write what the theta value in here, right? Any signal can be represented in this case with the m1 times cosinus wt plus phi 1, right? This is our case. It's the phi 1 and m1, and so just remember that in the S-plane we have the only poles that determine to the output characteristics of the R system representation. But this is just root, just like this one. This is the S-plane. We can select the pole or place the pole by using the sum methods. If this is the case, and so every system can be represented with its magnitude value with the sinus or cosinus values of these terms. Okay, and so how we can emulate these concepts in here? Just remember the MCK system in here: spring, damping, and the M force value. And so Ft can be equals to the Mi times cosinus Wt plus phi I. This is the phase representation. And also we can say that right now Xt must be equals to the M output magnitude cosinus Wt plus phi 0. Phi is the phase, okay? And so this representation can be summarized with with these nominations. And so if we have the input in here, just like this one, Mi W with some phi I W, this is the phase, this is the magnitude of its terms, and then we can use the R system is also its frequency, natural frequency. Just remember that in the second order equation, and also a phase deflection in here, just like this one. And so we can generate the R response with M0 W with the phase angle of the 0 phi 0 W. Okay, and so the idea is simple. We can select any sinus signal in the S-plane with in terms of its magnitude and the phi value, phase value, just like this one. This may be sinus signal, okay? And so the R system is represented in the time domain or in the S-plane as the poles, just like this one. These two poles, the R system. And so we can write the two magnitudes in here or the one magnitude in here to build the whole this notion. And then we can generate another magnitude in here, the output magnitude. For example, this is the M0, okay? This is the basic condition of the R term. But how we can visualize these results? Just see that if we apply the outputs can be summarized with the 1. For example, if we apply the Ft signal in here in time, Ft, and so we can use the sinus signal in here, just like this one, okay? And so we have the magnitude value in here with the sum phase, the input phase, okay? This is the input phase. And so also we have the magnitude value Mi in here. And then how we can generate the output value in here? The output can be written or drawing with the concepts of the Xt in here for the system output. And so if we have this notion, and then we may have this utilization in here. But what is the magnitude of these terms? The magnitude of the M0 is equals to the Mi times M. right? Because in the vector notation, just remember that in the S-plane, we can build the what or concept or multiply scalarly these vectors to what? To build the main vector, right? It's the simple case for this one. And also in the frequency domain, we have an advantage of the what? The 0, phi 0 phase must be equals to what? The input phase and the system phase. Okay, and so this is the system phase and this is the input phase. Okay. So now if we have the input phase or input signal in here, this is the input signal, this is the output signal, we can write it right now. MW must be equals to the what? The M0W divided by MIW. See that this is the output, this is the input signal, and we can generate the what? The R magnitude at each frequency values of these terms. And also we can drive the phi W value in here, which is the phase, and so with the what? The phase 0 W minus phi I W. Okay, and so what's the meaning of this? This is the magnitude frequency response in here. Okay, and this is the phase frequency response. Okay, so if we have the W value starting to 0 to 100 values, for example, this is the radian, okay, divided by second, and so 1 by 1, and so at each case we can have the what? We can characterize the R system based on these two formula, the magnitude of the frequency response or the phase frequency response in this case. And so if we analyze the R system at each frequency coming from the input and the output signal, and we can design the R system based on this information, because we are dependent on the what? The changing frequency values at the input and the output, because the S-plane dictate us that if we have any frequency input and then your system is filtering them or increase them or decrease them based on the what? Based on what is the value of the applied frequency. Okay, and so this means that if we have this information, and then we can write the reminder right now. 1. Even if our system is perfect or perfectly controlled by the PID or any other techniques, it cannot response everything. Due to the what? Due to the low pass filter characteristics, because it's just kind of filter. It gets to what? To some input and transform to the another input, for example the voltage to position or the velocity, and then it generates to the what? Then the new ones. Okay, but in the nature or the control theory perspectives, the frequency basically determined, or the natural frequency is directly related to time constants, and it prevents the system to take movement at every frequency. This can be explained with the what? With these times. For example, we have the time constant for that tau in here, and so the steady state can be reached in here at the 4. For example, this is the 4 second. And so if I apply the ft, the input signal, as just like this one, this is what? This is the 4 Hertz sinus signal. In this case, if we apply this signal, and then this system cannot be response or reach the steady state value in here, because if we increase the values of these terms and then the application of this signal at the xt could be this kind of signal, okay? And so it cannot reach the steady state values of these terms because we cannot catch up to what? To the input signal. And so this is the frequency response of the R system. Even if we are system with a perfectly designed in controller, and then we cannot drive the R system based on the what? Or the beyond of the some frequency, which we call it to the what? The cutoff frequency. Okay? This is the simple example about the what? About the these things. And so we can conclude that we have frequency limit. In here. Okay, guys? So how we can demonstrate that? First of all, we need to write the MATLAB code in here. This is the MATLAB session, okay? So we can create the new script in here, and then weak or frequency response examples, clear all, close all, CLC, where one frec response .m, okay? I'm sorry, this could be changed, okay? So in the first example, we need to talk about the x0 frequency response problem, okay? So define the system just like this one. The num is equals to the 9, then is equals to the 199, and g can be defined with the tf, num, and then, okay? And so if I run this code, we have the 9 divided by s square plus 9s plus 9 system, okay? And so how we can show the R problem, frequency response problem in here? For example, we can define the time vector in here just like this one, t 0 0 0 0.001 and up to 10 seconds, okay? This is what the timeline for the definition of this system. For example, w1 2.pi.1, okay? And w2 is 2.pi.2. This is the 2 hertz. And w5 is the what? 2.pi.5. This is the angular frequency of these terms, okay? And so the input 1 hertz can be defined with the what? The sinus signal w1 times t. This is our signal to be applied to the system, okay? And so we can copy off these things in here. This is the 2, and also this is the 5 and 5, okay? And so the output 1 can be obtained with what? The LSIM function. We can provide the system in here, the input 1 hertz can be given, and the timeline should be given in here, okay? These are the basic utilization of the what? The simulation performance, okay? and so the output 2 G2 and output 5 and input 5 should be given in here. Okay, so we should draw the whole parameters in here, the t and the output 1 Hertz. This is just like the step response, but in this case we need to apply the sinusoidal signal. Okay, and so if we want to do that, we need to give the system input or the user defined input and the timeline. Okay, and so it generates what the output response of the R system G. Okay, and so this is the B, and display name should also be given in here as a legend 1 Hertz. Okay, this must be 1 this time. Okay, and so hold on. We should copy off these things in here just like this one, and so this is the red and this is the green. Okay, and 2 Hertz and the 5 Hertz, and the legend must be show, and X label is the time and Y label is the output of the R transfer function. Okay, and so title can be given different sinus inputs. Okay, and so if I run this code, I'm sorry, the output 1 Hertz, output 1, output 2 and output 5. Okay, so grid on must be also given in here. So at this case, just see that we have a perfect system in here, because if we utilize the watt, the figure step G in here just like this one, and then see that the G is going to the watt up to 1. At the steady state it's perfect, right? We are closing to what the final value as the 1, and so we can reach the steady state value at the rate of the water settling time, which is in here the 3.5 seconds. But if I apply the sinus signal in here, this perfect system, just see that 1 Hertz creates the what, this amplitude values in here, just like this one. Up to what is the 0.15 to minus 0.15. See that if we have the perfect system to this one, and so the steady state error must be 0, but in this case we cannot do that. Just see, we have the 0.85 error value in here. This is unacceptable for our case, because our amplitude must be what, plus 1 to minus 1, right? And so what about the 2 Hertz? The red line is the 2 Hertz, right? And so this 2 Hertz is smaller than the what? Than the blue one. If this is the case, the R frequency is increased or speed up, and then the R magnitude is slower than this one. This is the error case for the what? For the application of the frequency response, but it's coming from the nature. We cannot do that. God made it, and we need to deal with it in the universe, especially for the design the control theory. Okay, and see that if we increasing the another signal up to what, up to 5 Hertz, and so this is what the amplitude of the what, the 0.007. This is so small with respect to the what, to the 1 times sinus 2 times pi times 5 times t signal. See, this behaves like the what, the low pass filter in here, just like this one. And so this is the what, the error is case for the what, the frequency response analysis. And so what's the conclusion is that the conclusion tell us to what, even if we have the perfect system, perfect controller performance, we cannot drive or track any signal with the frequency domain. And so we need to apply, or we need to study about the frequency response techniques to the control system, especially in the transfer function domain or the S domain. Okay, this is our problem, guys. In the next session, we need to talk about how we can analyze the different frequency in terms of the magnitude and the phase response in the frequency response analysis. Okay.